In the vast, indifferent expanse of our solar system, danger often hides in plain sight. In January 2023, astronomers detected a small asteroid mere days before it brushed past our planet. Known as 2023 BU, this truck-sized rock passed just 3,600 kilometers from Earth, closer than many satellites. It had approached from the blinding direction of the Sun, evading every ground-based telescope until the final hours. Ground telescopes can only hunt at night and must look away from the Sun. Any object arriving from that forbidden solar vector remains invisible until it is dangerously close. 2023 BU proved the point. An amateur in Crimea spotted it on January 21st. 5 days later, it screamed past at record proximity. No one had seen it coming from the Sun's glare. We possess the power to deflect asteroids, yet we remain blind to the very ones that could arrive with almost no warning. This is NASA's hidden vulnerability, the sunward sky threat, and it is far larger than any single close call. On January 21, 2023, Gennady Borisov, an amateur telescope maker in Crimea, captured a faint moving point of light. Within hours, the Minor Planet Center confirmed a new near-Earth object. By January 25, NASA issued a public alert. The rock would pass Earth the very next day at just 3,600 kilometers. Objects between 5 and 50 meters across strike Earth statistically once per year at the small end and once per millennium at the large end. Yet current surveys miss most until they are inside the orbit of the Moon. 2023 BU was one of the closest non-impacting approaches ever recorded, and it arrived with almost no warning. The event exposed a structural flaw in planetary defense. We can now deflect asteroids with kinetic impactors, but we cannot reliably find the ones coming from the Sun's direction in time to use that technology. The blind spot remains. Ground-based optical telescopes suffer from a permanent blind zone surrounding the Sun. They cannot observe during daylight, and even at twilight the solar glare overwhelms faint moving objects. Any asteroid whose apparent position lies within roughly 40 degrees of the Sun stays hidden from every major survey. Asteroids on certain Earth-crossing orbits naturally approach from this sunward vector. Their reflected sunlight is lost in the solar corona. Thermal signatures are also difficult to separate from daytime sky brightness. The result is systematic underdetection of an entire class of potentially hazardous objects. This is not a small gap. It is a structural vulnerability in our entire detection architecture. Until we place sensitive infrared eyes above the atmosphere and outside the Earth-Sun line, we will remain partially blind to threats that could still arrive with almost no warning. In 2022, NASA's DART spacecraft successfully changed the orbit of asteroid Dimorphos. For the first time, humanity demonstrated it could deflect a celestial body. Yet that triumph exposed a deeper problem. We can hit what we can see. We still cannot see everything that matters. Congress ordered NASA in 2005 to find 90% of asteroids larger than 140 meters by 2020. That deadline passed unmet. Smaller objects in the 5 to 50 meter range that can still devastate cities remain mostly unknown, especially those arriving from sunward trajectories. The paradox is stark. We have proven we can act. We have not yet proven we can see in time. The next scene in this story is not another close call. It is the engineering response designed to close the sunward blind spot forever. February 15, 2013. A 20-meter asteroid approached Earth from the direction of the Sun. No telescope saw it coming. It exploded over Chelyabinsk, Russia at 30 kilometers altitude. The shockwave shattered windows across the city, injured more than 1,500 people, and caused $33 million in damage. The object came from the sunward blind zone. Ground surveys operating only at night and away from the Sun had zero chance of detection. It was a once-in-a-century event statistically, yet it arrived with zero warning. Similar objects pass undetected every year. Chelyabinsk proved that even modest objects can produce regional devastation. It also proved that our current architecture cannot guarantee early detection for the entire threat population. The Sun continues to shield a dangerous fraction of the sky. Many threatening asteroids do not begin their lives near Earth. They originate in the main asteroid belt and are gravitationally perturbed inward by Jupiter and the inner planets. Venus in particular performs a delicate yet deadly ballet, nudging objects into orbits that repeatedly cross Earth's path from the sunward side. These resonant interactions can place asteroids on trajectories where they approach Earth while the Sun lies almost directly behind them. Reflected light is lost in solar glare. The mathematics of orbital mechanics therefore conspires with observational limitations to create systematic blind spots. Understanding this gravitational choreography is essential. It explains why certain objects remain hidden until the final hours and why simply building more ground telescopes will never fully solve the sunward threat. A space-based infrared solution is required. Scientists estimate roughly 25,000 near-Earth asteroids larger than 140 meters exist. Fewer than half have been discovered. For smaller objects in the city-damaging range, the catalog is far more incomplete, especially for dark low-albedo bodies and those arriving from sunward directions. Many asteroids are as dark as charcoal. They reflect almost no visible light. Ground optical surveys therefore miss them even when geometry allows. Only infrared detection of their thermal glow can reveal these hidden members of the population regardless of approach angle. The combination of sunward geometry and dark surfaces creates a double blind spot. Until we deploy a dedicated infrared space telescope positioned to stare into the Sun's vicinity, we will continue to underestimate the true population of threats that could still surprise us. NEO Surveyor is NASA's answer to the sunward blind spot. The first space telescope designed specifically to hunt potentially hazardous asteroids and comets. It will operate from the Sun-Earth L1 Lagrange point nearly 1.5 million kilometers from Earth, where it can continuously scan regions ground telescopes cannot reach. The spacecraft carries a 50-centimeter telescope paired with two infrared detector arrays operating at different wavelengths. By measuring thermal emission instead of reflected sunlight, it can detect both bright and dark asteroids and determine their sizes with greater accuracy than optical methods alone. A 20-foot-long sunshade protects the telescope from direct solar radiation, allowing it to look closer to the Sun than any previous mission. This single engineering feature fundamentally changes our ability to monitor the previously forbidden sunward sky. The Sun-Earth L1 point is a gravitational sweet spot where the pull of the Sun and Earth balance. A spacecraft placed there remains stable with minimal fuel. From this unique vantage, NEO Surveyor can observe asteroids both leading and trailing Earth's orbit, as well as those approaching from the Sun's direction. Positioned sunward of Earth, the telescope gains an unprecedented view into the inner solar system. It can detect objects whose orbits keep them interior to Earth's path for long periods. Precisely the population most likely to approach from the blind zone. This strategic location combined with infrared sensitivity transforms Planetary defense from a reactive ground-based enterprise into a proactive space-based sentinel capable of providing years of warning instead of days. The 6-meter sunshade is the largest and most critical structure on NEO Surveyor. It blocks direct sunlight from entering the telescope aperture while its sun-facing side carries solar arrays for power. Without this shield, the infrared detectors would be overwhelmed by thermal noise from the Sun itself. The telescope itself operates in two mid-infrared bands. These wavelengths allow detection of heat radiated by asteroids warmed by the Sun. Because the measurement is independent of reflected light, the system performs equally well on dark and bright objects and can operate even when geometry places the target near the Sun. This combination of massive sunshade, advanced infrared detectors, and L1 positioning gives NEO Surveyor the unique ability to systematically search the sunward sky for the first time in history. It is the engineering solution to a problem centuries old. Behind every pixel of data and every line of code stands a team of scientists and engineers. Amy Mainzer, principal investigator of NEO Surveyor, has spent her career hunting asteroids in infrared. Her team at JPL and partner institutions have turned an ambitious concept into flight hardware. Tarek Daly of Johns Hopkins Applied Physics Laboratory captured the stakes clearly. We do not know where most asteroids capable of local to regional devastation are located. NEO Surveyor exists to change that equation and to give humanity the warning time it needs. These are the modern guardians of Earth. Not warriors with weapons but scientists with telescopes and trajectories. Their work transforms statistical risk into actionable knowledge and gives our species a fighting chance against an ancient cosmic hazard. When NEO Surveyor reaches L1 and opens its eyes, it will stare directly into regions previously forbidden. Mission simulations show it detecting hundreds of new, potentially hazardous asteroids in the first years alone, including many previously invisible sunward objects and dark asteroids missed by all-ground surveys. Each detection will include not only position but thermal measurements, allowing rapid size estimation. This characterization data feeds directly into impact risk assessments and deflection mission planning. Knowledge becomes power on a planetary scale. The first light of NEO Surveyor will not be a single dramatic image. It will be a steady, relentless cataloging of the unknown. Each new entry in the database is one less blind spot in humanity's defense of its home world. Over its 5-year baseline mission, NEO Surveyor is expected to dramatically increase the known population of near-Earth objects. It will find the majority of remaining asteroids larger than 140 meters and provide critical statistics on the smaller city-damaging population that currently hides in the sunward glare. Particularly important will be the detection of dark low-albedo asteroids and those on orbits that keep them near the Sun for long periods. These objects have been systematically underrepresented in current catalogs. NEO Surveyor's infrared sensitivity changes the equation completely. The harvest will not end with discovery. Precise orbits and physical characterization will allow rapid assessment of any future impact risk and provide the years of warning required for effective deflection campaigns. Detection alone is not defense. NEO Surveyor's data will feed directly into NASA's Planetary Defense Coordination Office and international partners. With years of warning instead of days, humanity can execute kinetic impactor missions like the proven DART concept or future, more advanced deflection techniques. The combination of space-based infrared discovery and demonstrated deflection capability creates a closed-loop protection system. No longer will we face the terrible choice between knowing too late or being powerless to act. Both eyes and hands will finally work together. This is the future NEO Surveyor makes possible. Not the elimination of all risk, the cosmos is too vast for that, but the removal of the element of surprise from the most preventable natural disaster humanity faces. NEO Surveyor is not the end of the story. It is the beginning of a permanent, vigilant posture. Future missions may improve on its design, but the principle remains. We must watch the sunward sky with eyes that do not blink and instruments that do not fear the glare. The Sun will continue its ancient work of hiding threats in its light. Asteroids will continue their gravitational dance through the inner solar system. But humanity will no longer watch from a position of partial blindness. We will see, and seeing we can choose to act. The Skylab continues its silent patrol. The blind spot shrinks. The shield strengthens. And on this fragile blue world we sleep a little more securely, knowing that somewhere between Earth and Sun, an infrared eye stands watch against the oldest threat in the solar system.